All right, so now we're going to finish our Chapter 5 tutorial by looking at Cayley diagrams. A Cayley diagram is a graphical representation of the information that's contained in a group. And the way we construct them is relatively straightforward. We give a node, or a point, or a vertex, whatever you want to call it, for each element of the group. And then, leaving each node, we add one arrow per generator of the group, which points to the result of right multiplication. I realize that's a little bit of a mouthful, and this relatively simple I don't want to say two-step, but two-feature description is a little bit misleading, I think, in the sense of it doesn't fully show the complexity involved in constructing a Cayley diagram. So what we're going to do with the remainder of this tutorial is do basically two examples of Cayley diagrams. Now, before we get started, I want to just give a little disclaimer, which is that while the first of these examples is pretty simple, not so hard to come up with what the diagram would look like, in general, it's not so easy to just know the answer to these kinds of questions where someone gives you a group and they say, what does a Cayley diagram look like? While working this out for this tutorial, I think I've tried, I'm going to say 3 different times now, to make this Cayley diagram look as simple as possible. And so while it's not so bad to figure it out with some trial and error, I don't want you guys to think like I'm just coming up with this on the top of my head. I just know what it looks like. If you have to draw a Cayley diagram, you should go get your marking whiteboard or your blackboard, behind you, and be prepared to do a little bit of messing around before you get it right. Okay, so let's take a look at our examples. First example, very simple. We're going to look at a cyclic group generated by one element and no relations. So last time we had relations like a squared equals e or b cubed equals e, and that's going to be the other example we look at, but no relations here in particular means the only power of a, which is equal to e, is n equals 0. And so to draw this, we have to start by coming up with what are the elements of this group. And we saw last time that this will consist of the powers of a and their inverses. Like so. And every single one of these guys gets a vertex. I mean, I'm not going to obviously draw you infinitely many, right? But we have, we might line them up in a line like so. And then the deal is from each node, we add one arrow per generator of the group, pointing to the result that you get when you multiply on the right. So if I do e times a, I get a. If I do a times a, I get a squared times a cubed, and so on. And going backwards, well, if I was going to draw an arrow like so, I would have to know what element, when multiplied on the right by a, gives e. That would be a inverse. And so this might give you a reason to think about like why we played this game in the other problem solving sessions and in the homework regarding solving equations in groups. It's very reasonable to know I have some element of a group, maybe it's b, right? B times what makes this other element c? How do I populate my Cayley diagram correctly? There's no b and c, so I'm going to erase this in this example. But you get the idea that like working out what I need to multiply by what in order to populate the diagram might be something that you're interested in. And when you're done, when you have a finished diagram, this one's relatively straightforward. We've seen before that this guy is kind of reminiscent of the usual number line. Reminiscent, yep, that looks like it's spelled right, of the integers. When you have a finished diagram, the diagram tells you pretty much everything you could possibly want to know about how to combine elements in the group, because I can just see what happens if I, for example, take any element of the group and multiply it by any generator. If I have an element that's not a generator, well, I figure out what that element is in terms of the generator. And for a cyclic group, this is maybe not the best example. We can't really see because there's only one generator, but I can use this information and I can deduce that I have this chain-like property analogous to the number line. Let's do a more complicated example and you'll kind of see what I mean when I say it encodes the structure of the group. Let's look at the group we looked at last time. That group had two generators and it was subject to some rules, such as a squared equals b cubed equals e. And I don't know if we said this previously, so it's worth it to take a moment and just point out some terminology. When you have this situation where an element to a power gets you back to the identity, we call that the order of the element. So we would say that A has order 2 and B has order 3 because, e.g., b cubed equals 3. There was one other rule, which was BA equals AB squared. And putting it all together like this sort of representation is kind of analogous to set builder notation, right? We have the base objects that we're allowed to work with, the generators, and then the rules they have to satisfy, which are the relations. So you might think of this as kind of like a group builder notation, like compact representation for a group presentation. Okay, so now let's try to make a Cayley diagram for this group. Now, like I said, I've tried this a couple times and I think I've figured out the best way to do this, but I didn't know until after I'd messed around and gotten some bad diagrams a few times. And the first thing that stood out to me is that because I have this order 3 element, order 3 generator, b cubed, I'm probably wise to start with a triangle. I'm going to try to draw this kind of big so we have room to make the picture clear. So here is E, and then multiply by B to get to B, multiply by B again to get to B squared, then multiply by B again to get to B cubed, but B cubed is E. So at this point, we know what the elements of this group are. We wrote them all down. Maybe we write them down again over here on the side. We had E, A, and B, and then we had AB and AB squared, and also just B squared by itself. So right now we have 3 elements of this group. We need to populate the diagram with 3 more elements of the group. Well, the easiest way to get started is to try to see what I should do to add arrows leaving these elements representing, well, multiplication by A. And because I want this diagram to encode what happens when I multiply by A and B, I'm going to use a different arrow for multiplication by A. I'll use a dotted arrow. If I have a lot of different kinds of diagrams, a lot of different kinds of generators, I might want to use maybe multiple colors or other kinds of arrows. Maybe we get a little creative. In any case, when I multiply E by A, I get to A. But when I multiply A by A, I actually get back to E. So this should be a double arrow. Now I have to figure out what to put on these guys so that this diagram works out as cleanly as possible. And for that, well, probably the thing to do is to try to multiply B by A and then place its A piece, right? Its A arrow over here. If I multiply B by A, we have in our rules that this is equal to AB squared. So how about we make this one AB squared? and we have an arrow going this way. And now, because I have this rule, I can actually infer what happens when I multiply by a again. This, we might not feel like we know what it is. Looks complicated. But ba squared, since a squared is equal to e, that's just b again. So you see this arrow is also a double arrow. It's not too hard to convince yourself then that exactly the same thing happens over here, although, and we know what element this has to be because I got e and b squared and ab squared are all in the picture. So the only one not in the picture yet is ab. So this really has to be ab. And it has to be a double arrow. But let's check anyway. We do b squared times a. Let's calculate what this is. This is ba. ba equals ab squared. So we get bab squared. Here I have another ba. Change that to ab squared as well, times b squared. This is ab to the fourth power, which is the same thing as b times b cubed. B to the third power is e. So we get ab. So our diagram is coming along now. All of the outer vertices indeed have two arrows leaving them. E goes to a and b goes to b squared and ab squared. B squared points back to e and it points to ab. And I have the 6 vertices, but these vertices do not have arrows leaving them. Or rather, they don't have second arrows leaving them. They have one arrow pointing back. So what I have to do is I have to multiply by a on the right. That gets me ab, which points up here. ab points to ab squared. And then ab squared points back to a because you get ab cubed, and b cubed is the identity. So you see, this picture is a pretty nice little diagram with solid lines. Maybe we didn't write a little legend for this anywhere, but we have solid lines for B and dotted lines for A. And we basically came up with this. I basically came up with this by trial and error. I mean, I know there's a diagram in Pinter's book that looks a lot like this, but I wasn't going to copy the diagram just blindly, right? I needed to think it through for myself so I could explain it to you guys. And so that involved, well, starting with basically just guessing and trying to see how you might come up with this shape by, well, trial and error. In my first attempt, I had these guys placed wrong, and then I had to figure out why. And so it takes a little bit of elbow grease. Now, to wrap this up, I made this comment before that I was saying that having this Cayley diagram tells you everything that you might want to know about how the group multiplication works. And in order to illustrate that, let's take a simple example. So we'll scroll down just a little bit so we can still see our diagram. You can see all the nice labels. Just a bit more, please. Not that far. Okay, my scroll wheel doesn't want to let me do it. We're stopping here. Let's do a multiplication, a non-trivial multiplication. Let's start with the element AB, and then let's multiply by one of the other group elements that seems complicated and is not a generator. So how about AB squared? What you notice is at every step, we are multiplying on the right. So what this means is we start with this guy, and then we first multiply by A, and then we multiply by B twice as we work to the right. So I start with AB, and then I have to take the A arrow. A arrow lands me up here. And then I take the B arrow twice. So I go over to E, and I go over to B. So the diagram seems to tell us that this gets B. We should probably verify that. So let's do some calculation and see if we have AB squared. There is a BA in here. BA is equal to AB squared. So we have A times AB squared times B squared. This is collecting the terms a squared times b to the 4, and a squared is e, and b to the third is e, which leaves a single b left. So you see the Cayley diagram, it captures all the same information as the group multiplication table, except, well, the multiplication table is way more annoying in the sense that if I wanted to fill out the multiplication table, I would have a 6 by 6 table. So 36 entries I have to calculate one by one. On the other hand, if I have a nice Cayley diagram, like so, this has the information of the multiplication table, but I don't have to work through each and every element. We're exploiting the fact that we have learned about subgroups of groups, and we've learned about, in particular, group presentations to break down any element of the group into its components and then follow this like a map to get to the destination. And overall, that's just going to be much, much more effective. The difficult part, of course, is if you have very little information about a group, making the Cayley diagram can be tricky. But for as we're going to see throughout the remainder of these chapters on group theory, there will be a good number of groups for which we will be able to understand them reasonably visually, reasonably quickly, and we'll unearth that as we keep moving forward.